Hello friends, welcome back to Quantum Quandary. Today we're going to derive the area of a circle. Now we do know that the area of the circle is supposed to be pi r squared, where r squared is the radius of the circle. But let's see if that's true. So the way we're going to start is we're going to take a square and we're going to put a circle inside the square. This is called inscribing a circle. We inscribe the circle such that the sides of the square A are tangent to the sides of the circle, to the arc of the circle. So this is R and this is orthogonal. That's what it means for the lines to be tangent. And we know that the area of a square, I'm going to denote it by A4, is A squared. So this is our first approximation. The area of a circle is A squared, where A is the side of the square, and we would know that A is 2R, so that would mean that A4 is 4R squared. Well, 4 is sort of equal to pi, right? Not really. Close enough. Well, we need another approximation. So why don't we double the side of the angles? No, the number of sides. Why don't we double the number of sides? This isn't really a nice octagon, but it's supposed to be, what is it ever even called? The equilateral? The one with the equal sides, right? So you've got to inscribe the circle. Okay, I've got to make a better one. Like that, and you inscribe a circle. Again, this is R. And we can see now that there's much less, so to say, empty area. So here we're making an error, right? This is all the error. Whereas here, we only have errors here. And as we increase the number of sides, we're going to have less and less errors. Now, of course, I don't know the formula for the area of an octagon by heart, but we're going to derive it now anyway, so let's see. What's really nice about all entagons is that they're made up of tiny little triangles. So we can take out this one triangle that we drew here. If I draw just these sides, we had a triangle like this. And we have another triangle like this. Oh, like this. Let's just make that look a little nicer. Since it is supposed to look geometrical, like that. So these are the 3 consecutive sides of our octagon. If we just limit ourselves to this and this, we would have a half and a half here. Okay. Now, we are going to treat this triangle, this blue one. We're going to call its area S, okay? So its area is S. But to find its height, we're going to look at this triangle, the red one. We're going to look at the red triangle, which is obviously just half of S's area. And in the red triangle, which I'm going to draw here, we have R, we have the hypotenuse, I'm just going to call that H, and we have a half. Okay, that's pretty clear. Another thing is we know this angle. We know, let's call it, actually, if we look at this big slice, if we look at triangle S, which is double the size, right? We notice this is A. And if we call this angle alpha, we know that there's 8 A's in an octagon. Rather, there's n A's in an pentagon. Then that means in the octagon's case that alpha is 2 pi over 8. So it's an eighth of a whole circle. And in the case of an pentagon, it would be over n. So alpha is 2 pi over n. Okay. And from here, this angle is just half of alpha, because as you can see from the red triangle and the blue triangle. All right, so alpha over 2 is just pi over n. Alpha over 2 is pi over n. And now from here, we want to get a as a function of r. Well, a as a function of r, from this triangle, we know that a half over r is tangent alpha over 2 from this one. Well, if we just rearrange everything and plug in for alpha, we get that a is 2r times tangent pi over 2. Now I'm going to denote a with subscript n. So let's add that right here. A subscript n is 2r tangent pi over 2. Now let's have a look. For example, a3 would be 2r pi over n, sorry, would be 2r tangent pi to the pi over 3. Tangent of pi over 3 is square root of 3. So that would be 2r square root of 3. Now, of course, for a triangle, equilateral triangle, we have these kinds of radii. If we look at one of these segments, it's pretty well known, I guess, that that the height is a square root of 3 over 2 of the whole triangle, and then r is I believe it's 1/3 of h. But let's make sure that that's true. Let's make sure that that's true. So we've got this is 2 pi over 3. Like this, so we've got an r here. So this is pi over 3, and this is a half. So from there, of course, tangent pi over 3 is a half over r. Yep. So that's fine. That's fine. And our area, in this case, our big area, A3, did I introduce this notation? I didn't. I did with A4. Okay, so our big area, A3, in this case, oh yes, I didn't yet introduce what the area is in terms of these slices. So let me just erase this then. We don't really need it. I was just trying to show that this holds. But a big area, AN, is just n times the number of slices, Sn. Actually, n is the number of slices and Sn is the slice. So Sn is this blue triangle. And then AN is the whole area of the antagon. So n times Sn is how many of these blue triangles we have in our whole antagon. And one area Sn is just A. It's this side, right? Or let's use this triangle. Let's just rotate it to look nicer. So this is A. This is the angle alpha, which means that this is R. Yes, that's R. Which means that Sn is just AR 1/2, right? The way I always remember this is you can complete a rectangle, and so this is A times R, but only half of it because you don't have these halves. Okay, so 1/2 AR, but we know that A is a function of R, so Sn is R squared tangent pi over n. Now this is looking more and more like a circle, isn't it? We would just need this to be equal to pi, and we'd get a circle. well, we need this to be equal in there. So an is equal to r squared n tangent pi over n. Yes, so we need this to be equal to pi for this to be a circle. Well, like we said, we're looking for an infinitesimal length of a side of an entagon. So what we want is some sort of entagon that would follow the whole circle. So then this area would completely match. Now, of course, this entagon has infinitely many sides, so we just need to find the limit as n goes to infinity of an, and we think that this is going to be the circle. Well, that's nothing but r squared times the limit as n goes to infinity. Now I'm just going to multiply with 1 over here, and of course 1 is just pi over pi tangent pi over n. Okay, now I want to look at this quantity. I'm going to take one of the pi's out, so I'm going to have r squared pi r squared limit n goes to infinity, and now I'm just going to kind of manipulate this a little, write it like this, pi over n. Oh, my pi is disgusting. Pi over n. So you can see I just took this n down to the denominator and then made the inverse. And now I'm going to call this quantity t. And we're going to check what t is. So we want t to be equal to 1, and it is going to be equal to 1. And we're going to get our circle then, but we don't know that yet. So the limit is tangent pi over n over pi over n. Let's n go to infinity. Well, this is a case of 0 over 0 as we write it, right? So as n goes to infinity, tangent pi over n goes to 0, and so does pi over n. Now, this might be a familiar expression for those of you who know sine x over x goes to 1 as x goes to 0. But even if we don't know that, we can just express tangent as sine over cosine first. And cosine pi over n is just cosine of 0, and that's just 1. So we can forget about cosine. Let's just write that though. So sine pi over n times 1 over cosine pi over n. So this goes to 1. Then sine pi over n over pi over n. We can use L'Hopital's theorem, which says that if limit of... Oh, I guess we really shouldn't use L'Hopital's theorem if it's discrete. But we don't have to. We can treat it as continuous. Yeah, I'll just use the L'Hopital's theorem. It's fine. We can expand it in linear order. We could expand sine pi over n in a Taylor series. And then just omit. Yeah, we can do that. Sure, let's do that. This is a physics channel anyways. So sine pi over n is pi over n minus pi over n to the third. 1 over... Is it 1 over 3, 1 over 6? We never go this far, do we? Whatever it is, should be 1 over 6, right? 3 factorial. But in any case, I'm just going to omit this because it tends to 0 as n tends to infinity much faster than this does. Even if I don't omit it, it'll just be limit of n tends to infinity of, so if I plug this in, that's just 1. And then minus 1 over 6 pi over n squared, and plus blah, blah, blah. Okay. Now, obviously, this all goes to 0 as n tends to infinity. So, we're left with 1. So that's equal to 1. T is equal to 1. So, the limit, n tends to infinity, of an is just pi r squared, which is the radius of the circle. So, when you have an entagon, as n tends to infinity, the area of the entagon tends to pi times r squared, where r is the radius of the circle that's inscribed inside it. i.e., we just showed that the area of the circle is equal to pi r squared. Well, that's it for this video. Yeah, it's a It's a pretty long one, actually. It was supposed to be much shorter since it's much simpler, but I hope you guys liked it. I was gonna beg for likes, but I'm not gonna do that. So yeah, see you guys in the next one. Bye bye.